Okay people, you probably prepared this nice and green material, which is tetrachlora complex of copper, and it's at the moment in this distorted square planar geometry, and it's got green color. So what you can do is this: you can heat it up to about 65 degrees, and we're using hot stage, and this speed of the hot stage is at 65 degrees at the moment. So look what happens. So we are putting it on the hot stage, and heat goes through the glass and starts to heat our sample. The sample is being heated to 65 degrees and change color. On chemistry level, what is happening, the geometry of the platinum of the copper complex is changing from distorted square planar to distorted tetrahedral geometry, and this affects the homoluma gaps and therefore the color. So this is a reversible transition. We can cool the sample, and hopefully we'll see that the color will be restored back to green. So in this case, we are using our eyes as a spectrometer, but here at Northumbria we've got far more sophisticated spectrometers, so the Kate will demonstrate.
Okay, when you do absorption spectroscopy in the lab with the UV vis machine, you're normally using a liquid in a cuvette to find out what the absorbance is. You shine the light through it, you measure what's absorbed by your sample, and measure what's left over. If you've got a solid, however, it's not quite so easy to shine a light all the way through it. It would just get blocked by your sample. So we have to have a little bit of different setup to use. Now, in the lab, your spectrometers usually see big, huge machines. In my lab, however, they're a lot smaller. This is actually the brains of the operation. So the fibre optic is measuring all light coming into the spectrometer, splitting it up on a diffraction grating and measuring it on a camera, which we can see displayed on the screen here as a spectrum. Our light source, just a simple tungsten halogen lamp. Effectively, it's a light bulb in a fancy case with a port on the end to stick a fibre optic on. The bit that does the measuring and what you're actually measuring is done by reflectance. Now, the design of this is based upon the alignment principle that was used on the Lancaster bombers for the dam buster raid. Go check your history books, guys. So we have two beams of light coming in either side from our light bulb, and where those two beams cross coincides exactly with where we're measuring from the centre fibre optic. This one goes back to the spectrometer and measures all light that's reflected from this point here. You obviously need a reference sample, something that says I am completely white light, and this is what we use. It's called spectron. It's the whitest substance known to man. It's a really, really white PTFE. So if we put that underneath our sample, align it so the beams cross, and you've got a single spot there, we know we're measuring 100% white light from there. You tell the spectrometer that that is 100% white light, and then it will be able to measure the light that's reflected relative to that. Just like when you get a transmission spectrum, it's not in the absorption spectrum that you normally see. You might remember from atomic and molecular interactions, I have done a lot about this. Reflectance gives you very much the same thing, so you have to do a little bit of maths to transform it into the absorbance spectrum that you all know and love. All you do is you plot log of 1 over the reflectance values, and that'll give you a true absorption spectrum. Now, if we're going to measure our sample, the advantage of this equipment is we can put our hot stage underneath there and focus the beam of light directly onto the sample. Okay, now spectroscopists usually work in a blackout room. The reason for this is that our spectrometer is so sensitive, it's picking up the peaks from the lights above our heads. The peaks that you can see here are due to the chemical compounds that coat the inside of the light bulb and emit the light that you and me see as a white light. It's not really, there's actually peaks in there that are particular to those chemical compounds. So, lights off. Now the lights are off, we have a flat line on our spectrum because we're not picking up any of the ambient light, it's dark. Eureka moment. What I'm doing now is I'm telling the spectrometer that that is dark, and we can subtract whatever the readout noise is from the spectrometer as a dark spectrum. I then need to tell it what is pure white. So I'll put my spectrum standard underneath there with the light focused onto it and tell it that that is white light. Now the spectrometer will measure everything relative to that white light source. So now we put our compound onto the hot stage with our beams of light focused onto it, and we're actually measuring the reflectance spectra of it. As that compound heats up, changes geometry, changes colour, obviously the HOMO-LUMO gap is changing. Remember that this also corresponds to the energy in terms of light. So if we think about that in terms of wavelength, we see a shift in the maximum peak of our reflectance spectrum that we measure.